Good afternoon, everyone, and welcome to the fourth and final ProClimate Knowledge Zone session. Today we have Jason Quinn from Sustainable Engineering presenting on E3, internal moisture, and G4 ventilation. Jason, welcome.
Thank you.
And just as people load into the webinar, let me recap on the last three sessions. So far in our sessions, we've covered B1 structure combined with H1 energy efficiency. That was last Tuesday with Rob and Ryan. That session, along with the others, is on the ProClimate YouTube channel already. And if you just search ProClimate Knowledge Zone, you'll get there. On Wednesday, Dr. Anthony Pelosi from Victoria University talked us through the challenges of succeeding in ventilating our buildings adequately to meet clause G4 ventilation while considering pollutants both in the air and in the materials we build with, which of course may off-gas into the air. And that session, his case study gained a lot of attention and questions. On Thursday, we saw a speed demonstration of a significant piece of ongoing work that MB Brands and the Window and Glass Association have in play. The technical manager of the Window and Glass Association, Rob Campion, was presenting. He opened up the development of acceptable solutions and our favorite E2AS1. Our favorite, that was some sarcasm from me, the acceptable solution for window install at the time didn't take into account H1, but it did a good job of E2. And those clauses were the focus of where Rob is currently working to change the accepted and acceptable window performance for all our buildings, which brings us to today. And we welcome Jason Quinn to the stage. Jason's like an expensive hard cheese, sharp, occasionally offensive. He can slice through a thermal bridge debate faster than you can say air tightness. Since 2007, he's had roots here in New Zealand, long before building science-led design became fashionable. And it is fashionable, right, Jason?
It is.
Jason's been pushing for better, healthier, more comfortable buildings for a long time, with the big idea that buildings should actually look after the humans inside them. Please welcome Jason Quinn. Jason, you are presenting today on E3, internal moisture, and G4 ventilation. First question, which these two, they seem like a basic idea. Why is it so hard?
It's fundamentally so hard because we still think we're in the 1920s and pretty much everything has changed, both the people inside and what we do in our homes, how we manage our homes, what we build them out of, and how our homes work from ventilation and internal moisture is totally different, but we haven't updated our thoughts on that since then.
Well, Jason, I'm going to interrupt you just a couple of times along the way, maybe to ask you to slow down, or maybe clarify something, or bring a question or two from the audience. So at that point, I'll turn my camera off and it's over to you.
All right. Thank you, John. I appreciate that. So this is a topic that's near and dear to my heart, and certainly one we work a lot on in our company. Just to kind of give you a bit of background on myself, I work for Sustainable Engineering, the founder director. We've got a staff of about 6, and we focus on high performance and passive house homes in general, as well as we do quite a bit of work on larger buildings, doing natural ventilation studies or modeling of all sorts of different things, whether it's zonal modeling or that kind of thing. And we tend to work on research projects with the industry when we can. For example, the High Performance Construction Details book, which was done with Fins and Brands, and we're currently working on a retrofit book with ECA and NJGBC, so that's good. So that perspective from the industry kind of gives us an access to a lot of different buildings, both current buildings that need to be retrofitted, existing buildings, and of course new buildings being designed. So we've got a pretty good perspective across what happens in residential space in New Zealand. So from that privileged space, I wanted to talk about buckets. That's gonna be the theme of the presentation, and it'll be really obvious what's going on in just a second, I promise. But I do want to try to have a theme in presentations to kind of people on cue. So see if you can follow the buckets through this presentation. It will stop at some point, I promise. All right, so G4 and E3, ventilation and internal moisture. These two things are treated in their building code as separate things. And at the code level, at the top of this triangle where we've got this little top where it's the Building Act and the building code, it's actually pretty well stated. Like when I've been to international conferences, people look at our code from overseas and they're like, wow, you're so lucky, you're from New Zealand, you've got a performance-based building code. where they've thought about it at the top level, and you've got all these great stuff. And it's true. For G4 and E3, the top level building code says basically keep buildings dry and healthy and comfortable with fresh air and low internal moisture. That's what it says. Basically, the top parts of that pyramid. And you can't argue with that. That's what they're supposed to do, right? And the only part you can argue about is that they're treated separately, whereas they're very heavily integrated. And we'll see that on the next slide. Unfortunately, when we step down to the next level of the pyramid, where we're talking about acceptable solutions, the acceptable solutions in New Zealand for G4 and E3 are not designed to provide good design guidance or produce good buildings. They're just supposed to tell you you're not allowed to building worse than this legally. Like literally will arrest your ass and lock you up if you make a building that's worse than this. And when I look at the acceptable solutions, to me, they look very much like placeholders. Like 20 or 30 years ago when they wrote this stuff down, they're like, oh, I'm not sure what we should do just yet. We know this isn't going to hurt, like as in this won't make a good building, but this isn't too hard and you at least should do this. So we've got requirements for our values from E3 internal moisture and overflow requirements for liquid water. And then G4 ventilation, we've got this intermittent requirements for rates that the building could ventilate at, not that it actually ventilates at that. And the bottom line is these requirements are so poor in the acceptable solutions that I really think they're borderline gross negligence at this point. We know that they don't produce good buildings in general across our stock statistically, and we know that because we can look at numbers of buildings with mold and building surveys and see that. So bottom line is G4 and E3 at the top level make really good sense. When you step down to acceptable solutions, it's really bad. And part of the problem is the reason it's so hard to build buildings that don't mold in New Zealand is because we think that these provide good guidance. And in my opinion, the acceptable solutions do not provide good guidance, right? So why do we care? Like, why do we give a shit, right? So we care because if you think about the things that produce a healthy building, and I really like this graphic, which is from the Harvard, I think it's a public health school from Harvard, and they've got what they call the 9 foundations of a healthy building around this circle. And 5 of them, so more than half, are basically covered by G4 and E3, right? Ventilation, obviously, that's G4, ventilation. Air quality is covered by G4 and E3. Thermal health is actually mostly covered by E3 in our code, believe it or not. E4's H1 is all about energy efficiency, not thermal comfort. Then moisture is obviously covered by E3 because that's internal moisture, and perhaps by E2. And then dust and pests, which is very much a function of E3, because if you have high internal moisture loads, you get lots of issues with dust and pests. All right, so we care because we all have this vision of producing buildings for our clients that are healthy. They're kind of in that Goldilocks zones where every day feels like a nice, fresh spring day where it's just nice and comfortable all the time, all year long in that home, right? That's what the vision we want to have for our clients. And we can do that, but we don't generally. You want homes that dry themselves. Like I remember a long time ago, must be 8 years ago now, I heard a building professor from Auckland somewhere talking on a radio show about high performance homes, passive-house, I think he was talking about. And his thing was that his shtick was that these homes are so great that they just dry themselves. The towels in the bathroom just dry themselves. And that was because he was talking about a home that had a mechanical ventilation system, which was running all the time. And to him, that was an amazing thing. And the reality is we can make all buildings be that amazing. And it doesn't necessarily have to cost heaps, but it does require us to think more about it in our design process. And it's something you don't see, so clients don't see it. They would feel it when they're in the building, but by that point, the building's built and they're in it, all right? So it's really important that the reason we care about this stuff is because we want to produce amazing buildings for our clients. People even live in them, right? People are paying for them, and they're paying quite a bit, right? So what's the tragedy? The tragedy is that G4 and E3, first of all, this dealt with separately, and the acceptable solutions for me are, I could be kind as in the 1950s, but I'll say in the 1920s. So those assumptions built into that code are assuming that there's a continuous ventilation rate just by leakage to the building. And that has not been true since at least the 1950s, maybe even earlier than that. Once we switched away from literally strips of wood for flooring and horsehair plaster, horsehair plaster on lath walls, we don't have enough infiltration to the buildings to make them work, right? So as soon as you went to gypsum board and plywood, you have buildings that do not ventilate enough. So we can do other things, but that's one of the biggest tragedies, right? So G4 and E3 assume that we control moisture inside with ventilation rates. They assume that that ventilation is acting on average over the whole year enough to keep the air fresh, and that'll then in turn control interior moisture and allow reasonable enclosure not to mold. And the real tragedy that's built into there is that they don't do that, right? And we know that because if we look at building surveys from the brands does across the country every few years, which is a huge service. I'll complain about brands later on a little bit here and there, but they do a huge amount of service to our industry. We see that like half the buildings mold, right? So that's the tragedy. And the real tragedy for us as design team, is working on design teams, is that people look at G4 and E3 as good design, and they are not. They're just the worst you're legally allowed to do. If you did it even a tiny bit worse, you wouldn't be able to sell the building. You'd be arrested as a designer, right? So as people who care about clients and the buildings we're designing, you need to design for a dry home with fresh air, even when the occupants misbehave in a reasonable way. If you've got a young professional couple living in a brand new home in Auckland, for example, and they get the money to take showers and then go to work and lock the building up, that building shouldn't mold for that couple as normal practice. And it will now, because when they leave after they've taken the showers, if they don't have run-on timers for their exhaust fans, which they typically don't, they will not have a dry house when they come home. They'll have mold, right? And we see that happen quite a bit. And there's other issues as well. We'll get into that. All right, so how are we doing? In general, I kind of already jumped into this. We're doing pretty shitty, is honestly how it is as a buildings, right? So 40% of bathrooms had visible mold in them in the last, I think it's a 2015 survey brands did. So this includes a lot of what we would call modern buildings. There's a lot of roof challenges, let's call them that at the moment, that's happening with moisture in roof assemblies, which is interesting because people will think it's E2 sometimes, but it's usually driven by internal moisture, which is E3. And we're going to talk through those things. So this photo here is from a brand new house in Christchurch that is working well in some ways. So that window right there, that's the inside, and water's splashing off this tall window so much on the sill tray that it's actually splashing onto the sill, the timber sill, and onto the carpet. The carpet's actually wet in front of that window. And that's a brand new house that's been well built. It didn't leak. The night before it was sunny. It was sunny the day before and it was clear night sky. There was no rain. That isn't leakage. That is condensation on the inside of that double glazed window, right? It's not due to the cold frame. It's condensing directly on the glass. If you've got condensation directly on the glass, it means the interior moisture in that place is way too high. It is on the frame. We've got really poor performance frames in New Zealand in general. That could be just even relatively normal humidity would be fine. But this is clearly due to too high humidity in the home, right? So this home is not doing well on its own, right? So the one, go ahead, John.
But I've got a question. I'm glad I jumped in right there because that home you've just had, image on screen, yeah, is that not the occupant behavior kind of issue? Like, what's the, if that was a tenanted home, I know where the blame would be landing. So is that not a ventilation issue?
It's not a tenanted home, and it's a brand new home. And I happen to know the person who took this photo because he's a friend. And he just woke up in the morning and took the photo, right? And they clearly had the house all open the day before because it was nice and sunny. So that condensation is from the moisture in the home from that evening. I don't know about you, but if you're in a city, you don't always sleep with all the windows open. And in the wintertime, I tend to close the windows. So I would argue that it's a poor design practice in that there's no way to ventilate that home continuously while you're sleeping, right? Because if you don't ventilate this home, you get these kind of moisture buildups and you get this kind of condensation. So I'd argue it's not an occupant, it's poor design practice of building homes that do this normally. Okay?
Right, I just have one, yeah, go on, keep going.
Okay.
So I just have one other sort of statement question around this. You've used the phrase buildings mold and don't mold. So that's a new kind of way of just, two words rather than lots. Where is that from? Is that something that you've made up to describe? Is that international? Where's that phrase, don't mold or buildings mold, meaning buildings grow mold? I just haven't heard that phrase. Is that?
I think it's just me trying to shorthand things. Sorry, I wish there was an international standard. I'll look later. Maybe there is, and I just picked it up.
Great, good. Right, I'll get out of the way.
It may have been something that Dr. Joe Stubrick has said from Building Science Corporation, United States, that I've just picked up. Yeah, there's lots of people I respect around the world that I would have tried to copy the language at one point or another, so that's possible there. Yeah, so the, okay, we'll leave that there. I will say one part. So I remember walking around a hardware store in New Zealand when I first shifted here a long time ago, and seeing those window vacs where you can suck the water off the window, and just thinking that was just amazing. Both because it's horrible because you have to vacuum your windows, and two, that they had such things. And I know that when we had a bunch of building scientists over from Canada, they actually bought one to give to them as a gift because they were just they just thought it was hilarious to bring back to Canada, right? As sort of a gag gift. Because you wouldn't design your buildings so that you normally had condensation on the windows every day. It just seems kind of crazy to folks from other developed countries. So, all right, let's move on to the next slide. So this is about one of the biggest things that's hard to get across to people, even people building really expensive high performance homes or trying to do high performance on a budget. It doesn't really matter who. This whole idea that you need to ventilate and heat to dry out a house. And we'll actually go into this in quite a bit of depth because it's basically, if you get this one thing in your head, then everything else just sort of makes sense. And you can design buildings that kind of meet G4 and E3 pretty easily if you get this fundamental concept, right? So we ventilate for a couple reasons. And I know that, we had a presentation earlier this week, or last week, I'm sorry, that talked about internal air quality and off-gassing for materials. And the original ventilation rates that we use that are in G4 were actually developed in the United States many years ago, and then developed from basically stinky stuff, right? So ventilating enough so your house didn't reek was basically what they were designed for. And it turns out that those same ventilation rates, if we take them just a hair in the United States, control CO2 levels fairly well if you actually ventilate those rates all the time, not with little squirrel fans you turn off with a switch, right? However, the way they work is you throw air out of the building or you push air in the building, it doesn't really matter. You change outside air to inside air. And the whole idea is you're doing that to dry out the air inside the house or to make the moisture inside the house lower. Right? If you take air that's outside in the winter in New Zealand, in most parts of the country, it's something like 80% humidity, right? And you want the inside of your building to be like 60% humidity, ideally, maybe even a little bit lower, right? So when you bring that 80% humidity air in from outside, it's winter, you bring it inside and you heat it up. And when you do that, it gets drier, the relative humidity drops. And we'll look at that in just a sec. Because you're bringing this air in, and because when you heat it up, its humidity drops, you can then use it to dry the home, right? And it's a moisture balance where you have a ventilation rate and you have outside temperature and you have inside temperature. And you're trying to basically run enough fresh air through the building to control the moisture level. Because like I said, this ventilation rate that's built into G4 is designed around how stinky things are and controlling for CO2 levels. But it doesn't provide ventilation with a looking at moisture generation and controlling moisture levels in buildings. Because if it did that, we wouldn't have condensation on double glazed windows. We wouldn't have as much mold in our buildings as we do now, right? So it's this balance. And I'll try to show you in the next couple of slides why you have to ventilate and heat. If you don't do both those things, ventilating doesn't necessarily fix it. The story I don't like to hear, one I was really saddened about, was talking about tenants. This whole question about, if that building, the photo I just showed you, the windows dripping, was tenanted with people renting it, in other words, they would blame the tenants, right, that they didn't ventilate enough. And the interview was of a student flat over in Te Aroha Valley here in Wellington, which is a north-south valley, so quite shaded in the winter. Basically, just parts of that valley don't see sun all winter, right? Well, to a good extent, right? And the students were basically saying, hey, we left our windows open all winter, like literally open, didn't even close them at nighttime, like literally left them open. I don't know what they do about security. Probably they just don't have anything worth sealing, right? So they have the windows open literally all winter and it's still moldy. And the reality is, since they left the windows all the way open all winter because they were trying to keep the house from molding, and they didn't bother heating it because the windows are open, right? So because they weren't heating the building, the inside humidity is higher than outside because they're still living in that space. And their body heat's not enough to heat it up because the window's open and it's an old villa. So they're basically causing the mold because there's higher moisture levels inside than outside. And outside, they're like 80% humidity averaged over the winter. And I'll show those numbers in a sec. So they didn't heat the air up, so it's not going to dry the space out. And if they're going to live in it, then they're going to have higher moisture levels than outside. So you've got to ventilate and heat. And that's something we'll go through now. So buckets. So this is where I was talking about the buckets analogy, right? So this is the way I know best to try to explain what's going on, because it is a bit techy, right? But basically, if you take a bucket of air, a cubic meter, it doesn't matter, any unit you want to use, a liter a second, a cubic meter, meters out, whatever units, I don't care. You just take a bucket of air, and you're in, let's start with Auckland, because it's got the most people in there, right? So if you look at Auckland, and you take a bucket of air, over the winter 3 months, it averages about 11.4 degrees centigrade and 82% humidity, relative humidity, right? Pretty humid. And you take that bucket of air and you bring it inside your home and heat it to 20 C. And this is one of the assumptions built into the building code, is that you will do that all the time, by the way. And the ventilation rates assume to be all the time as well, by the way. So you take that bucket of air, you bring it inside, you heat it to 20 degrees centigrade. What happens to the relative humidity? Well, it drops to 47% humidity level, right? Which is great, because we want to stay below about 60% to pretty much not have any problems with condensation on double glazing or mold in the house or other issues, right? So if you think about it, and you can see it in that picture there where you take the bucket from the left to the right, you can see it drops the blue part, the amount of water in the air goes down to 47%. And that means that if you want to throw the air out of the window when it hits 70%, in other words, you're going to use that air to dry moisture from a shower or cooking or breathing, and then you're going to keep the house below 60% ideally, but even below 70% is probably sort of reasonable. Then you only have a small amount of drying potential in Auckland, right? You've got that little red strip there. We've got that little margin of water. You can put more water in the bucket from interior activities, and then you throw that chunk of air out the window. So when you bring that air in and heat it up, you're actually doing a useful function. It's not being thrown, you're not wasting that energy by having that air leak out the building or get thrown up by an exhaust fan, right? It's doing a very useful activity. But you have to move the air through the building, i.e. ventilate, and you have to heat that air. If you don't heat that building, even if you have a passive house, even if you've got a passive house times 2 insulation and you got 5 panes of glass, I don't care. If you do not ventilate and heat the air up as it comes in the building, you could do it with heat recovery to heat it up, but heat the air up and keep the building at 20, you will not have any drying potential, right? If you didn't heat that air up, if you left that air at 11.4 degrees centigrade, it committed 80%, you'd bring it up to 90, everything would mold. It doesn't matter what kind of house you have. You have a passive house, living building challenge, whatever you want to have, it's not going to work. You need to heat the air up to provide drying potential to then dry the house out, dry all the stuff out. So if you don't heat the air up or you don't ventilate, you will have mold. It doesn't matter what kind of building you have. It doesn't matter how good you make the envelope. And that's one of those tragic assumptions built into E3 and G4. Like, they need to work together. And E3 assumes if the envelope's good enough, you won't have mold on the inside of the building. But the reality is that's dependent upon you keeping the interior relative humidity down. And we'll look at why things mold at certain humidities in just a sec, all right? So let's pick another bucket. Let's just jump all the way to the bottom of the page and look at Queenstown. So Queenstown in the winter, it's 3.6 degrees centigrade over those 3 months of the winter on average, and 76% humidity, but pretty close to 80%, right? You bring that bucket of Queenstown air and heat it up, and it's going to take more energy because it's going from 3.6 degrees to 20, right? So roughly speaking, it's going to take 4 times as much energy to heat it up, but you get a hell of a lot more drying potential, right? So in Queenstown, you're at 26% energy. You can see the blue line in that bucket. It's pretty small. So you've got twice the drying capacity in Queenstown, which means if you're ventilating for moisture control, which I'm telling you, this will be one of the conclusions from this presentation, and it's certainly a conclusion in our practice, then in Queenstown, you need about half the amount of fresh air than you do in Auckland, if you heat it to 20 degrees centigrade, right? And that's always perhaps not an assumption we can stand on in New Zealand, but it is an assumption that's built into how they've done the code, all right? So buckets of air. We'll talk more about buckets in a sec, but I'm going to show you a slightly different graph, and sorry, it's slightly more scary graph in a sec. So this is the exact same thing we're looking at here, buckets of air, just in one continuous graph. And it's called a psycho chart, or psychometric chart, to be really honest. So what this is temperatures on the bottom, right, 0 to 20 degrees centigrade, and absolute humidity is on the y-axis. And I've literally taken the numbers off to not confuse anyone, right? So basically, horizontal lines in this chart is a constant moisture content, right? So relative humidity can change as you go left to right, but the amount of moisture in the air stays the same, right? So if you look again, we've got the same numbers we just looked at. We just looked at Queenstown, so let's look at Queenstown again. So if we think about Queenstown, it's at, say, well, we said 40 degrees centigrade, roughly 3.6 centigrade, and almost 80% humidity, a little below 76%. And we just go horizontally all the way across, we'd say, well, if you dry it out, it gets to 27% humidity at 20 degrees centigrade. But if you only heat it up to 10 degrees centigrade, you're still below 60%. You've got drying potential. If you look at Wellington and you take something at 80%, and it turns out it's around 8 or 9 degrees centigrade, I forget, and you go across, it dries out nice, it's below 50%. But if you only heat to 10 degrees centigrade inside that Wellington house, in other words, you don't heat it in the student flat, then the humidity stays, it's like 78%. Everything pretty much molds above 70%. We'll look at that on the next slide, actually. So we'll talk about that in a sec. It's a few slides away now, but we'll talk about where you get mold on a surface. But the point being is if you do not heat the air up and you don't ventilate, you can't dry out your building. You'll get very high interior relative humidity. When that happens, you get condensation even on really well-designed enveloped things like walls and roofs and floors that are well insulated. And it's not because the building envelope quality is not good. It's because the interior RH is not being controlled. No testing on the psychometric chart. It can be confusing even for engineers. It's just a way to plot how things change with humidity and temperature. All right. So what do we do with tools? All right. One of the things we talked about when we were laying out these presentations is what we present to folks. So one of the things you should do as a designer of a building is someone on your design team should be doing a moisture balance, or have done a moisture balance on a similar enough building and actually looked at the numbers and decided for these kind of buildings, we're doing this because we've checked it and we know it works. So this is something we do on all our projects because we use Pass Files Planning Package version 10, which does a full moisture balance of a building. So it considers air leakage, losses, people in the building, internal moisture loads, and most specifically the climate in the building. And by assuming a heat to a design point, which you can put in, a temperature point, you can look and see how this dries out the building or not. And this moisture balance is actually quite a simple thing. You can do it in a dynamic way where it's hour by hour, but in reality, building materials and envelopes can, and mold itself, take time. So it is reasonable to use monthly averages, which is what we use in PHP 10. So this moisture balance lets you decide that if you're ventilating enough. In other words, the fundamental question, like, is there enough airflow to the building if I heat it to 20C, or if I heat it to 22C, or if I don't heat it, I'm only at 16C. And what you find is that you better be down on the South Island if you're not going to heat it very much. All right. So as part of doing those models, those integrated models, we do lots of different building models, ranging from single-family homes to apartment buildings, and look at different ventilation rates. We even do detailed zonal models. We're looking at heating, cooling loads, and ventilation rates, individual zones inside of buildings. And that sort of detail is not generally needed. What you need in general is an overall building model to look at overall ventilation rates for the building, make sure you've got some distribution of air to that building, either by extracting certain rooms and allowing air to leak in other rooms, or having balanced mechanical ventilation with heat recovery. Doing zonal models is usually done very late in detail design and with more complicated buildings. With our current trends of kind of big open plan living, one of the benefits of those is that you do get good mixing in the space. All right, now let's go back and talk more about how the interior relative humidity results in mold on a surface, because in reality, we want to control RH in the building so we don't mold the building, really is the main thing, because people are comfortable at all humidity, well, can be comfortable at most humidity levels, right? Having a high humidity environment, unless you've got some weird breathing disorder or something, you just do fine in the steam sauna, right? You can breathe fine. So what we're worried about is molding our books and our leather belts and our equipment we put in the attic, right? So let's talk about that. So imagine we've got a building and that it's in Queenstown, because that's how you get these conditions, right? It's 20 degrees C in this building and 50% relative humidity. That's relatively dry for most of New Zealand, which is why I said Queenstown. This is a common condition you'll have in winter in Queenstown if you have a good continuous ventilation system of many types. And then you basically have the air in the middle of the room is 20 degrees centigrade. You can measure with a thermometer. And you can, the same kind of thing, you get a little air on net thing, you can measure relative humidity as well, right? You can tell, like in my space right here, I'm at 50% humidity and 22 degrees centigrade, which is, they kind of go together, right? And you take that little particle of air and you imagine, and you're looking at a surface of a junction. In this case, you've got a exterior wall junction. This is a horizontal section with 2 studs and no insulation in that little corner. So if you look at the temperature on the face of the gypsum board inside that corner in a static way, you'll see that the temperature on that surface is just below 12 degrees centigrade in this imaginary time. It's probably 0 degrees outside in this model, right? And what you find is the RH, the relative humidity on that surface, because it's colder, is actually 83% humidity. So even though the center of the room's at 50%, the surface humidity is 83%. So in that room we looked at with a window with all the condensation running down that window, we know the relative humidity on that window surface was 100% because it was wet, right? We could see the water. And the interior room was probably more like 75% relative humidity. Could have been 80, but it was probably not below, it wouldn't have been below 60, it would have been 70 something percent, right? And that means that you got 100% on that surface. And that's what's going on. We're looking at the ways the temperatures control the surface. So even in a passive house, even in the highest performance building you can imagine, the surfaces of the exterior envelope will be colder than the inside when it's cold outside. Because even though the envelope is really well insulated, and let's say there's no thermal bridges, it's still going to be cold on the inside because that's how heat transfers from inside to outside, right? It's hotter inside, colder outside, and the surface will be slightly colder than the air in the room. So if we look at mold growth on a surface now, so now we've taken this bit of air in the middle of the room at a certain humidity. We're now looking at on the surface, we've got an elevated humidity, and we're trying to see how mold grows. And mold is pretty interesting. There's lots of things we can talk about, but basically what causes mold growth is 4 things we can control, right? There's temperature on the surface, or the temperature of the environment the mold's on, the surface it's going to grow on. There's moisture level. It does not require 100% humidity. Lower humidities work. Material, whether you've got paper-faced gypsum board or unpainted, untreated pine is probably the worst material. That's even worse than leather belts. It's a really good growth medium for mold. And then you've got time, right? So of those 4 things, time, moisture, material, and temperature, what can you control on that surface the easiest? Well, moisture is the easiest thing to control if the building's already built, because you can't really control temperature because the outside and inside is being controlled. You could heat the building up more, that helps. But you really can control interior moisture levels, or the moisture level on that surface, the most. So the graph on the right plots surface humidity on the vertical axis from 70% humidity up to 100, and then surface temperature on the x-axis. Right. So if you think about your surface we just looked at in the previous slide, it was something like 12 degrees centigrade. So it's here. So it says basically if you're above 80% on things like untreated pine or paper-faced gypsum board, that's not painted in this case, 80% humidity on the surface, you will grow mold. That's what it says, given a reasonable amount of time, right? And then if you have a medium resistant surface, like let's say, that Ceratone lining you have in bathrooms where it's like almost like looks like ceramic almost, but it's paper. It's anyways, or you've got a plastic surface or even glass, for example. You can see above 85% humidity, you'll get mold growth, right? So the easiest way to keep this from happening, to stay in this below these lines where you don't get mold, is to control interior humidity so that when we have a cold surface, it doesn't have a high enough relative humidity to grow mold. So I want to make sure that the most important thing you get from this graph is that you do not need to be wet to get mold. Even forever, you could never be wet and still get mold. You just have to have humidity over 80% or over 85%. Hey, John?
All right, let's dig into this a tiny bit.
Let's do that. We've got time.
Yeah, what you are talking about is our homes, right? This is kind of, it's not about design. It's about what's happening in our homes. My single glazed aluminium joinery from the 1970s currently has mold on the aluminium. Why is that? Because that doesn't appear to be particularly tasty for mold.
Because you have dust. So basically mold just needs RH and dust and time, right? And temperature. So your window frames are somewhere between 20 and 0, probably, being in Auckland, probably around, around outdoor temperature around 10, average over the winter. And so if the humidity gets high enough, and they probably even have water on them, but even if you pretend you ran the house dry enough, you haven't got water, you've just gotten above 85% humidity. So above 85% humidity, you'll get mold on the glass. Never mind on the frame. The frame's much tastier, easier than the glass. So you'll get, like, if you look closely at the windows in this house, for example, which is very dry, it's 50% humidity, you'll see that in the bedrooms where the curtains are closed, my son's room, almost all the time, being a video gamer, he is, you'll see specks on the glass. And if you wipe the window, you're like, oh, it's got dusty and dirty. No, that's mold growing on the glass.
Right.
Yeah.
Okay, so with that then, I sort of understand how moisture relates directly to dust. Maybe that's another question for later on. But prior to this, so if we're talking about now what we're designing, how or is it the responsibility of the designer to be kind of keeping the home dry? Is that, yeah, apologies, I'm sort of fabricating that question as I go.
Oh, no, I mean,
what do we have control over? Because it's the occupant who does the wetting part, right?
Do they? They just live in the home like an old person, right? So I'd argue that because our G4 solution allows us to just use fans on a switch, and our E3 solution, which is supposed to protect against interior moisture, isn't integrated with G4, that it's actually gross negligence on the designer's part, right? And the reason I say it's gross negligence is we know that half of our buildings have visible mold on the inside, right? If half of our buildings fell down on people just randomly as they lived in them normally, without them cutting any studs, right? We would say that that's not okay, right? Because they die right away. But mold in buildings just makes a fraction of our population sick, right? And results in us having to repaint stuff and damages buildings and cause costs and stuff. So it's slow and over time and gradual. So we don't count that. You're allowed to kill people if you do it slow enough.
Do it slowly. Yeah. Okay. Yep.
Yeah. I mean, it's like lead. It's like lead in gasoline, right?
Right. So we, that was a known problem which took a long time to remove. This is a known problem. And it's taking a long time to remove. So
and it still is, yeah. And you can sit down. I mean, I've sat down in rooms with some very smart people, and with government officials talking about these exact clauses, and you'll get people saying dumb things like, anyways, I don't want to get into that. I don't want to get people in trouble. We don't need to pick on people.
Okay.
People
I'll jump out. Let you keep going.
Yeah. But no, that's a good point. So as designers, the point I'm trying to make with these slides is that in controlling interior relative humidity is your responsibility. And you can do it easily with ventilation. And we'll start talking about now what you might do to do that in a sec. That's our next set of slides. Actually, I think it might even be the next slide. Let's jump to that. All right. Nope, it's not. Maybe we'll jump one. And it's actually 2 slides down. All right. So let's unfortunately introduce one more technical topic before we get to the answer, which is what do I do with ventilation in buildings, right? So when we're talking about buildings and we're looking at, we've taken this block of air that's at 20 degrees centigrade and 50% humidity, moved to a surface where it got to 80% humidity, which we see from that chart is bad because even on our aluminum window frame and glass or junction there, we get mold, right? Even on a surface that's resistant to mold resistant paint, right? Unless it's got some kind of fungicide or something in it. So how do we look at that across building envelopes? The way E3 does it is it has this, you can't have an R value worse than this kind of thing. And there are ways to use that exact metric in a very logical way. But in an attempt to keep the building code simple and easy to use, in my opinion, we've not done that. We've just got an E3 metric, which is, well, I'd say it's almost nonsensical. All right. So a metric that's used in other building codes, and I'd recommend we introduce in our building code because I think it's an easy one to understand, is this thing called FRSI, right? And all it is a ratio, how cold does the surface get relative to the difference from inside to outside. So if it's 0 outside and 20 inside, an FRSI of 0.5 says it's halfway between, which is 10 degrees centigrade. If it's an FRSI of 0.75, it's 3/4 of the way to the hot part, so it's 15 degrees centigrade on that surface. So it's an easy metric, right? So if we take a building and we ventilate at a certain rate, in this chart we've got a ventilation in liters per second per person because that's what the building code uses. And the building code, by the way, says we should have 7.5 liters per second per person, but only when the fan's on, which is a bit weird. If you've got windows. If you don't have windows, you got to do continuous ventilation, right? The reality is you need continuous ventilation all the time. I mean, if you're in the house, you're breathing. If you're not in the house, you probably just took a shower and you're leaving and it needs to dry out the shower. So if we could look at the ventilation rates and we can look at this moisture balance using past soft-time package inside the building for different climates and say, okay, if I've got a certain ventilation rate and I'm heating the air up to 20 degrees centigrade, how good does my envelope have to be, right? So in general, I'll kind of jump to the solution, which is, in my opinion, you want to have something where you have an FRSI of about 0.5, right? And that says basically you could have a surface that's halfway between inside and outside temperatures, and you wouldn't get mold on it, right? And so this, yeah, that's the right way to say it. So if you think about these curves here, these curves are, the gray one here is for Queenstown. So that says basically for Queenstown, if you're ventilating at code ventilation rates continuously, not by turning the thing on and off, like you put a continuous extract fan in, or a balanced ventilation system in, or mechanical ventilation with heat recovery, and you're ventilating at 7.5 liters a second, which is in theory building code minimum, but actually ventilating at the rate, not pretending, like really serving your clients properly, then in Queenstown, what that says is basically you can have normal constructions and you won't get mold on the inside face of the building if you ventilate properly and you heat, right? So to me, that is the definition of a building that a designer's done a good job, because if the person lives in it without being an absolute jerk, like they're not running a sauna inside their house or turning off the ventilation system and trying to dry laundry, they're just doing things normally living in their house, then the house basically has reasonable requirements on the envelope without molding. So you won't get mold unless you do something dumb. And it has to be like really dumb, not just normal behavior, right? Whereas right now, in my opinion, the building code is set up so that if you behave in your house normally, you will get mold, right? Which is not good design. It is a legal code minimum. So unfortunately, if you look at this blue line, which is Auckland, and then the orange line is Wellington, because that's where I live, and you try to follow those down to see what kind of ventilation rate you'd need, in Wellington, you'd need something like 12 liters a second per person, continuously, heated to 20 degrees centigrade to keep that building dry, not 7.5. So either you need a very good envelope with really good details, or you need higher ventilation rates. Luckily for most of our designs, and unfortunately it was luck early on in our practice, still can be sometimes, typically our homes, we are ventilating around 12 liters a second continuously in our designs, right? So we're actually at this point where we're down, for a normal building enclosure, we get enough ventilation. However, we have had projects where they've got higher density or clients that misbehave, and in my opinion, they're not heating the building at all, and we've explained them they need to heat. They can mold anything, even a passive house, right? It depends, they need to ventilate and heat. Right? So this says you need higher ventilations, maybe 12, and for Auckland, maybe you need something closer to 14 liters a second. Now, if you bring that up amongst a bunch of building science geeks, they'll be like, oh, don't tell anyone that, because they'll use more ventilation, dry their house out and not have mold, but they'll use more energy. Yes. Also, if you're looking at mechanical ventilation with heat recovery in Auckland, you shouldn't be using 7.5 liters a second a person. You should be using like 14, right? Which means that you'll find that you'll use twice as much energy. Mechanical ventilation with heat recovery would make economic sense in Auckland. But again, because we tend to use G4 and E3 as a design target, or much of the industry does, and the acceptable solutions of those things is what I meant, not the code clauses. Because we tend to use G4 and E3's acceptable solutions as a design target in the industry, it tends to make us make really dumb choices. And that's the tragedy of it, right? So this is a graph to look at how ventilation rate would occur to get your surface temperatures. The point being, if you want to try to get the line across around 0.5, so it tells you the ventilation rate around 7.5 is pretty good for Queenstown, but you probably need something like 12 in Wellington and maybe 14 in Auckland to get the same drying rate and having an envelope requirement that's reasonable. What happens if you don't have a client that's not going to heat? Just can't afford to heat. Like, they love you, they wanted the right thing for your design, they love the building you designed for them, they're in it, and this mortgage is just killing me, I just don't have any money, sorry, just something happened, right? So either they need to figure out a way to ventilate more or heat, or they should expect mold, right? They're going to need to compensate for that. So if you think about what happens to these curves as to what the FRSI on the surface would be permitted, they go up and to the right, which means that the envelope has to get better and better, and above about 0.7 is just not realistic, right? So if you wanted to hit that 0.5 again at 18 degrees centigrade, you'd see you need to ventilate for Auckland, because these three lines here are all for Auckland, you need to ventilate at something like 20 something liters a second per person, right? Which is a ginormous rate, right? If you wanted to be at 16C, I think you need a ventilation rate of like 70 liters a second, which is insane, right? And that's because if you're not going to heat the air up, there's almost no drying available, right? 16C is still a little bit of heating up. If you have the same temperatures outside, or you're not going to heat it all, it doesn't really matter how much you ventilate. Outside air has got enough moisture in it, you're going to mold inside your house. So, all right. So what makes sense for ventilation? Sorry to make you wait so far in the presentation to get that. In my opinion, 7.5 liters a second a person continuously in the summer and down south makes sense. You could use CO2 control. In other words, the requirement to control CO2 levels in a home below 1,000 ppm. I guess I shouldn't say requirement. Quality standard to control below 1,000 ppm, and moisture control match down south, and they match throughout the country in the summer. And up north in the winter, Auckland, Wellington, you need higher ventilation rates and heating, right? I've got full tables of this as well as references to all this technical stuff and these slides available if you want it as a PDF at our website, KZone 2025, if you want that, because folks often ask for the slides afterwards. So I forget to save myself some emails. All right, so ventilation, yes, mechanical ventilation is required. I do want to take a little bit of a left turn now in this presentation and talk about other things that E3 is supposed to control. So we talked about the RH inside the space and why ventilation and heating is so important and why mechanical ventilation, continuous ventilation is required. I want to take a sidetrack and talk about other things E3 is supposed to control. Did you need to jump in, John, or you want me to go ahead and just trek on and let you jump in?
I'm just keeping an eye on the time. We've got 13 minutes left, so you take your time. We've got a string of good questions which are sitting waiting to go.
All right, we'll kick through this pretty quickly. So E3 is supposed to control interior moisture, and oftentimes people, including myself, tend to focus on interior RH control for interior surface mold control, right? And ventilation and heating fixes that, but you also drive that moisture through the enclosure, mostly with air leakage, some of it through diffusion through materials, but mostly with air leakage. And I've got this good article which was picked up by a magazine in Australia, and it talks about control layers. And I think that that's probably one of the fundamental things that we can get into. If you don't have control layers and you have insulation in assemblies, you should be concerned. It doesn't mean you need something new, like gypsum board makes a great control layer. And walls, that's what we have for a control layer. In ceilings, gypsum board can also be a good control layer if you don't put holes in it. If you don't have good control layers, you can get moisture in your assemblies. There's a number of really good papers out there. This is a really good one from Brands, SR344. I've got links on that website link I just sent you, where they talk about moisture in wall assemblies. This particular building here is a very high performance retrofit. It's the only certified EnerFit project in the country, which I worked on. And this building, the reason I worked on it, the reason it became an EnerFit building was because when this building was purchased by the new owner, the underside of the cold timber membrane roofs was moldy, even though the building had louvered windows, was a beach cabin, and was left open a lot. And that molded because of the way moisture moved through the assembly and a lack of control layers, right? I sometimes get sent photos like this. I try not to share people's things that could be private, but these are posted on LinkedIn to the public, and I know Rob wouldn't mind or Jack won't mind. So this is quite a common thing where we get roofs with water on the inside. And 95% of the time, this is due to air leakage from inside the building into the roof space, right? And then it condenses on the underside of the paper under the iron. This paper is designed to absorb moisture and act like a battery and send it back and forth, but because the interior moisture level is not controlled and the airflow into the attic is not controlled into the truss space, they've got moisture problems, right? So think about control layers and think about ventilation. The other place is roof ventilation in those truss roofs. We're seeing a lot of issues with truss roofs in New Zealand right now, primarily because of air leakage into the roof space and because the roofers are making the roofs quite airtight. In other words, there's not enough ventilation in the truss space. There's actually not a requirement in our building code for this. I don't know why. In most overseas would require 1 in 300 of the ceiling area be ventilation area in the roof space. And Brands has, again, done really great research in this and published some really wonderful articles in this great picture of a moldy ceiling. And they talked about increasing roof ventilation, having better ceiling air tightness, and reducing internal relative humidity. So I think with that, we'll go ahead and talk off. I think that's that. We've just got resources available for folks, and that's that, John.
Brilliant. Look, there's some good questions here, Jason. Here's the first one. Although mechanical ventilation might be an easier option, do you think a good balance between ventilation and heating can be achieved by passive design without depending on mechanical ventilation?
Hell no. It's an idiotic choice. Sorry. It's clearly not possible. The UK has similar climates to us in a lot of ways. They've done a lot of work with trickle vents, and basically trickle vents only work if you've got a mechanical fan running. They just don't work otherwise. People need to breathe all the time, even when it's cold out and I've got the windows shut. Sorry, I wish it wasn't true.
Okay, I'm just going to jump to one. So it's kind of simple here. Is it 12 liters a second or 14 liters a second ventilation required all the time, 24 hours?
Depends what climate you're in. So from those whole house balanced ventilation numbers, in Auckland, 14 liters a second, continuous is the number, which is about twice what the building code requires.
Right. So we're not looking at code minimums. Cool. Okay, how can you control moisture in houses in which heat pumps are provided only in the living area and maybe bedroom?
Well, heat pumps don't ventilate in general. There are specialized models that do, but generally heat pumps just blow the air around inside the house. So it's kind of like, waving a fan around in a locker room. It just blows a stinky air around. It doesn't actually do anything in terms of ventilation. So you need to provide ventilation to the home that's separate from the heat pump. And the cheapest way to do that, not necessarily the best, but the cheapest way to do that is with continuous extract fans. That's what's been built into Homestar as a code compliance, as a compliance tool for that standard. And it's what's used in similar climates throughout much of the developed world. So that's the least you can do, in my opinion, is continuous extract fans. It's not ideal because they will depressurize the rooms that have those fans in them, like the bathrooms, and they'll draw that air throughout leaks throughout the building, right? Generally under the garage, the door to the garage is one really bad space they draw air from. Obviously balanced ventilation, mechanical ventilation with heat recovery would be much better. But fundamentally, the extract fans is the way most folks tend to go because they're almost no net cost.
Right, but we've got to treat a heat pump as a heater, not a ventilation. It's not ventilation. So it's not ventilation.
Yeah. It's okay. It's okay if my mom thinks that, but an architect or designer shouldn't think that, right?
Oh, I know teachers who think that. Yeah. In fact, that's one thing. I mean, a lot of us have kids at school. Our school classrooms are atrocious for that. They've got heat pumps running on the wall with the windows and doors closed, so there is no ventilation. It's a comfortable temperature. It's maybe a comfortable humidity, but it is stinky. It is CO2 laden air. It's not being ventilated. It's a massive problem.
Well, it'll be really high relative humidity in the winter. It's only in the summer that they'll provide any sort of drying, because you're right, if they're conditioning the space, if they're cooling the space, they can dehumidify it. In other words, they can drop water out and then let it drain outside.
Right.
But in the winter, they cannot dehumidify. They don't have that ability.
Okay, can you just run a heat recovery unit without heating the space? Well, that's an interesting one. Given heat recovery doesn't, okay, let's just start with the first bit. Can you just run a heat recovery unit without heating the space?
Yes, you can turn the switch on and just let it run. What you're asking, I think, is does it control RH? So if there's enough internal loads in the space, like if you've got a gaming computer in every bedroom in the house, like I do right now, then you'll have enough internal loads from all those computers running that the space will be 20C with heat recovery ventilation only in much of the country, because that's quite a few watts. If you don't have enough heat in the space because you've got, let's say, a retired couple that doesn't like gadgets, for example, they have very few gadgets in their house, they won't have enough internal gains in their house to keep the house warm with just the heat recovery ventilation, so they'll need the heat as well.
Right. Heaters on thermostats. All right, let's change tack a little bit.
Ideally.
Would you do modeling? And I'm just assuming in the position here, it's passive house planning package modeling for normal houses.
Yes. And even for older houses built to an even poorer standard, we often do PHPP models.
Yeah. So understanding what you have if you're looking at a retrofit, understanding what you will build if you're building new, regardless. So it's not actually about passive house, it's about modeling.
Yeah, it's just an energy balance model. It's an easy one. So Echo by New Zealand Green Building Council is another good tool that's used a lot. We do use in some of our projects, mainly because somebody's asked for an Echo model for a home star rating. So they just do an energy balance on a monthly basis.
So the Echo model, that's free?
It is not. You have to be a home star designer to access it.
Right. Is PHPP free?
No, it is not. It's $600 for a lifetime license, so it's not very expensive, but it is not free.
Okay. If your air barrier is on the outside and you are seeing condensation on the glass, does that mean that moisture would also be condensing in the insulation layer of the wall, since that is where the dew point is?
No, that's not necessarily true. So if we imagine a wall which has, let's say, wood fiber insulation on the outside layer, Pinex, somebody's got Pinex on the outside and it's got ventilated cladding over the outside of that, you could easily have a setup where you get condensation in your single glazed windows, actually even condensation in double glazed windows, but that moisture is not condensing on that Pinex layer or plywood layer. It's being absorbed into there and then dries out safely to the outside. I'm not saying it would, but it can be not an issue inside the wall.
Right, right, and clearly there's a lot of wriggle room. I can understand how that question might have been asked differently, you know, and the way that you've answered it, but that's all good. Let's go to the building code. Building code allows certain bad situations. Clients can legitimately ask for a code minimum design for budget purposes. Therefore, should we get rid of the acceptable solutions, E2, E3, G4 acceptable solutions?
Yes, I mean, what I'd actually prefer is we redefine the next level up, which defines what's acceptable. I didn't actually show that slide. I don't know if my slides can still be seen, but if you download it, you'll see I've got what I think are better definitions for those code clauses that clearly links the two of them and what I would consider to be acceptable. Because one of the problems of acceptable solutions is they often define themselves in a circular fashion. Like, this is acceptable because it's acceptable. And if you actually dig into the language, which is quite entertaining if you're an engineer, right? So the acceptable clauses need to be fixed. The thing is that as a designer, just because you're allowed to, I don't know, run over small animals on your way to work, you shouldn't go out of your way to swerve to run over small animals. It's just not a nice thing to do. So you shouldn't design homes at a code minimum if it doesn't cost your client any more, right? And oftentimes, if you're just switching from a on-off extract fan to a one that runs continuously, there's literally no cost. Like, you can get them for nearly the same price. Actually, sometimes you can get them for the same price. And the reason that there's a small premium is because we don't all buy them all the time, right? So on a house that's $200,000, which is about as cheap as you can possibly build a little tiny home in New Zealand, putting an extra $200 into the exhaust fan, or even sometimes less than that, seems like it's not a logical, like it's not a rational thing to say that you're going to not put that in. So that's why I say it's borderline gross negligence, because there's not actually any cost to the client on day one.
Right. Okay, let's jump a little bit. You mentioned that the FRSI should be a minimum of 0.5. Which standard, question mark, does that approximate figure come from?
No, it's not a standard. So 0.5 is, I can generally build assemblies that hit 0.5 that are cheap to build. So in other words, if you look at the way we build typical timber frame homes here in New Zealand, with thermally broken aluminum windows and double glazing and studs with no insulation in the corners, you can still hit 0.5, right? Timber slab edges, concrete slabs with no insulation on the outside of the edges, you can hit 0.5. In other words, I should design my interior relative humidity levels so that 0.5 doesn't make mold, right? So in other words, I can still build the same way I do now, but if I control interior relative humidity well enough, then I won't get mold in that house, right? Or I could take an existing house that's built already, not change the building, just control interior relative humidity with good ventilation and heating and not have mold, right? So yes, I can envision building much better buildings, and that's something we should talk about another day. But here I'm just trying to say we should define that building code minimum as buildings that take care of themselves and the towels just dry themselves, right?
Jason, we're out of time. Thank you so much. You've brought challenge and I think a lot of opportunity here. You haven't been soft, honest, for good reason. I think there's space to be designing better buildings. Thank you for your time put into this presentation, and yeah, to push our industry along a little bit further. Hey, look, I just want to say thanks to the Proclaimer team in the background making this work, so video and audio and question and collating and editing and uploading to our YouTube channel as well. And for everybody who's joined us today, I trust it's been useful. Please give us your feedback too, and ideas for the next Knowledge Zone series. And so thanks again, Jason, for your time today, and we'll see you all again sometime soon.
Cheers now. Goodbye.